Alright, in this final video we'll be looking at acid-base properties of salts. We'll do some calculations and determinations of how do you know if a salt solution is more acidic or more basic, and then we'll wrap it up by talking about different strength or acid strength trends. So if you've got a couple different weak acids, how can you tell if one's going to be stronger or weaker than the other? Alright, so with a neutralization reaction, when you mix an acid plus a base, you usually end up with water and salt. So at this point we need to define exactly what salt is. So salt is defined as a compound when the hydrogen of an acid is completely or partially replaced by a metal. And so again, these things are going to be ionic compounds, and therefore they dissolve in water. So the other thing to remember as you're looking at all this stuff is the auto-ionization of water, because sometimes that is going to be something that's in competition with the other stuff that we're working with. So don't forget about that auto-ionization of water. So these ions are going to have either acidic or basic properties in water, depending on what they are, and we call that salt hydrolysis. So hydrolysis just means in water. So anything that's hydrolyzed, you're putting it in water. So there's three different types of groups that we're going to be looking at. Salts that produce a neutral solution, basic, and acidic. So let's get started with the neutral solution. Okay, so salts that produce a neutral solution. The conjugate base of a strong acid has virtually no affinity for the hydrogens in water. So let's give you an example here. So remember the strong acids, they're on that list. If they're not one of the 7 that are on that list, it's not going to be a strong acid. And also remember that strong acids completely dissociate in water. So it's not that you have H+, or that you have HCl, it's that you have H+ and Cl-. So what we're talking about is that the conjugate base, so in other words, the conjugate base is this thing. Okay, this is my conjugate base. And it has no affinity for the water. And in other words, this chlorine right here, is not going to react with the water. So it remains a neutral solution. Conjugate acid of a strong base also has no affinity for a hydrogen in water. So again, if you have a strong base in the list, if you remember from the previous videos, it's going to be an alkali metal or those couple alkaline earth metals that we mentioned. Those also completely dissociate, so it's not that you have sodium hydroxide, it's that you have sodium ions and hydroxide ions. So the conjugate acid, the conjugate acid is this thing right here. So the conjugate acid is also going to have no affinity for the water. So the sodium is not going to react with the water, and so therefore it remains a neutral solution. And basically what I was just kind of saying is that neither of these are going to affect the concentration of H's. And if you remember from how do we calculate pH, it's a measurement of hydrogen ions. So if something is not going to react with the water or bond with the water, it's not going to affect the concentration of the hydrogen ions. Second group are going to be salts that produce a basic solution. So here's an example. And probably as we move through the next two types of salts, we're going to be doing some calculations just to kind of help you see why they do or do not have an effect on the pH. So the first group, salts that produce a basic solution. So here what we've got are the conjugate base of a weak acid. So remember from our discussion of what a conjugate acid, conjugate base were. And if you know something about the strength of the original acid or base, then you know something about the strength of its conjugate. So what happens when it loses or gains the proton? The conjugate base of a weak acid is a, and I forgot to change this in the notes, but it's on your notes packet. It is a strong base. It is not a weak base. Conjugate acid of a weak acid is a strong base. So it will have an affinity from the hydrogen, and it's going to take that proton from the water. So how does this work? How would you go about figuring out if this is a basic solution or acidic solution, and how would you figure out what the pH of it would be? So for instance, if we want to figure out the pH of a 0.15 molar solution of sodium hypochlorite, this is bleach, the Ka of hypochlorous acid is 3.5 times 10 to the 8th. So here we've got a salt. So this is the salt, where you've got a metal that has replaced the hydrogen ion. And then it gives you the Ka of its related acid. So what we're going to do is kind of solve this with a systematic process. first step you want to ask yourself, what are the ions? So we kind of write out our dissociation equation. So sodium hypochlorite, NaOCl. When we put this in water, when it hydrolyzes, it will split into sodium ions and the hypochlorite ion. So remember from the previous slide, is this going to have any affinity for the water? No, this is not going to have any affinity for water. Sodium is going to be a spectator ion, and if you think about it, it's kind of related to sodium hydroxide, which is a strong base. So this is not going to have any affinity for the water. So this is not the piece that I'm interested in. This, however, is going to interest me because this aqueous solution of the hypochlorous acid, it is the conjugate base of a weak acid. This is the weak acid, and this is its conjugate base right there. So since this is the conjugate base, it will take the H+. So this one will want to bond with an H+. So that is going to influence our pH. Oops, I didn't realize I already had that written in there. Okay, so the next question we got to ask ourselves, is this a Ka or is this a Kb? Okay, so Ka, remember, is our dissociation constant for acids. Kb is our dissociation constant for bases. So how do we figure this out? Well, when we take that OCl, we take that hypochlorous acid, and we react it with the water like it wants to, it's going to form HOCl, hypochlorous acid. But then it's also going to leave this hydroxide. And so this is actually, if we think of our equilibrium expression for this, make sure I just don't have that there. Okay, if we think of the equilibrium expression based on this reaction, I've got a hydroxide ion and an HOCl, the hypochlorous acid, and I write that over my hypochlorite ion. And if I look at this expression, even though this part is a weak acid, I've got hydroxide ions here, which tell me that this is actually a Kb expression. Now remember, when you write equilibrium expressions, you'd leave out the water. You're not going to put in the liquids. Okay, once you've figured out if it's a Ka or a Kb, then you're going to calculate your Kb from the Ka that's given. Now how do you do that? Well, that's where Kw comes in. If you remember, Ka times Kb equals Kw, and you know a value for Kw. So Kb is equal to Kw divided by Ka. The value for Kw is 1.0 times 10 to the negative 14th. The Kb value, or Ka, was given to you in the problem, 3.5 times 10 to the negative 8th. And so that gives me a Kb of 2.86 times 10 to the negative 7th. Okay, now that I've got my Kb, I can figure out my hydroxide concentrations, and that's what's going to help me figure out pH. So if you remember what our original problem is, we need to figure out what the pH is going to be of a particular salt. That's our goal. Well, to get to pH, I need hydrogen ions, but before I can get to hydrogen ions, I have to have hydroxide ions. So now we're going to set up our ice table to get the hydroxide concentrations. So what I'm going to do is I am going to, not do that. I'm just going to rewrite my equation, and I'm going to put in the water, and then we're going to set up the ice box from there so you can see all the pieces together. Okay, so this is liquid, this is aqueous, this is aqueous. Also make sure that you're balancing these things as you kind of go through, because that's important for ice boxes. But I've purposely picked things that are easy 1-to-1 ratios. Okay, so now we're ready to set up our ice table. So what do we use for concentration? Well, you go back to your original part of the problem. So the original part of my problem says that my solution of sodium hypochlorite is 0.15 molar. Well, if I look at my dissociation equation, and actually let me just kind of erase all of this so I can see my nice little typing there. Okay, if I look at all of that, notice that what sodium hypochlorite does in water is it splits into this, and we've already figured out that the hypochlorite ion is the important part. The sodium is going to be a spectator. So since I know my initial concentration of this stuff, 0.015, put in my units, so I've got my unit. Now the water part I don't really care about, so that's going to be blank. Initial concentrations of my products, 0 and 0. what's going to happen? How is it going to change? This is going to go down by x. This is going to go up by x. That's going to go up by x. At equilibrium, my concentrations are 0.15 minus x, x, and x. I'm going to set up my Kb expression, products over reactants. So I've already written the Kb expression back here. Okay, there's my Kb expression. But now I'm just going to plug in the numbers here. So x times x over 0.15 minus x. I'm going to set that equal to what I just figured out in the previous part of the problem, 2.86 times 10 to the negative 7th. Remember the little shortcut that we can take? We can basically ignore that particular x because the change of this is going to be negligible, so we can ignore the x in the denominator. That makes solving this a whole lot easier because now you got x squared divided by 0.15 equals your Kb value. And so you go ahead and you solve for x, and I came up with 2.07 times 10 to the negative 4th. Alright, so now what does x mean? Well, here's where your icebox. I want you to think less memorization and always consider what is the chemistry, what is happening, what does x mean? Well, x is my concentration of hypochlorous acid, but that's not affecting my pH, but x is also my concentration of hydroxide ions. So what can I figure out for my hydroxide ions? Well, I want to get to pH, but I can't do that quite yet, so I'm going to solve for pOH. If you take the negative log of your concentration of hydroxide ions, if you remember from the previous video, how do you calculate pH? Negative log of 2.07 times 10 to the negative 14th, negative 4th. Never mind, it's not the 14th, it's the negative 4th. I wrote it correctly. I do the negative log of that particular number and I get 3.7. So that is my pOH. Now once I know pOH, I can figure out pH because pOH plus pOH equals 14. So 14 minus 3.7 equals 10.3. And that is my answer. And again, as you're going through these things, always ask yourself, does my answer make sense? I mean, what do you know about bleach? It's a cleaner. You would expect it to be basic. And your answer would confirm that. Your pH is 10.3. What about salts that produce an acidic solution? Well, the process is going to be the same. And again, your notes packet is correct, but my slide is wrong. So let me fix that. Okay. Conjugate acid of a weak base is a strong acid. So it will donate a proton this time. Salts that produce a basic solution, you're looking for something that accepts a proton. Here we're donating a proton. What is the pH of a 0.5 molar solution of ammonium nitrate? And I gave you the Kb value of ammonia. So the relationship here, ammonium, ammonia, that's how the one relates to the other. So step number 1, what are the ions that are involved? So let's write this particular problem out. Apparently I didn't put that in there. Okay, so I'm going to take ammonium nitrate. And when I put this in water and I write out its dissociation equation, that's what I mean by what are the ions. Dissociate it. What do you get? And from there, evaluate what's going to affect the pH or not. So what's the thing that's going to donate a proton? Well, this cannot donate a proton. There's no H for it to give up. And it's related to the strong acid nitric acid, which also completely dissociates. So that is not going to be part of our problem. This is the thing that's going to donate the proton. So this will partially dissociate, giving off that H+. Okay, step number 2. Now let's react to this important species with the water and see what happens and figure out our equilibrium, if you will. Okay, because it's a weak substance. This will dissociate into the ammonia and the H+ ion. So this is aqueous, liquid, and aqueous. Now we've got to figure out, is this a Ka or is this a Kb? So given my equilibrium that I've set up here, let's just write our equilibrium expression and then decide from there if it is actually an acid dissociation constant or is it a basic dissociation constant. If it's acidic, you're going to have an H+. If it's basic, you're going to have an OH- up there. As an ion concentration. Because again, you're trying to figure out pH. So what affects pH? It's either going to be hydrogens or hydroxides. That's what we're looking for. So in my equilibrium constant, my dissociation constant, I've got H plus NH3 and the ammonium ion down here. This H plus tells me that this is actually a Ka expression, not a Kb. So the next step is, now that I've realized that what I have is a Ka, I'm going to have to get to Kb. And the relationship, of course, is Kw. So Kw is 1.0 times 10 to the negative 14th. My Kb was given in the problem, 1.8 times 10 to the negative 5th. And so that equals 5.56 times 10 to the negative 10th. Okay. Now I've got my Ka expression. Now I need to get concentrations. So I'm going to set up my icebox. And just for ease of everybody being able to see everything, I'm just going to rewrite my equilibrium. If you've got it in your head, don't feel like you have to, but I just forgot what my other product's going to be. There we go. Now let's set up the icebox. My initial concentration, that's going to come from the problem. That's going to come from right there. The 0.4 molar solution. Water, I don't care about, so you don't need any sort of concentration there. Initial concentrations of product are 0. I know that my change is going to be down on the reactant side, up on the product side. So then my equilibrium values, this is going to be minus x, that's going to be plus x and plus x. Now we're going to solve for x. To do that, we're going to set up our Ka expression. Back here, I've already written out my Ka expression, so I'm not going to rewrite it. I'm just going to plug in my values from the icebox. So this is going to be x squared divided by, oops, put a 0 there, 0.4, 0 minus x. And my Ka value, which I figured out just up above, 5.56 times 10 to the negative 10th. Again, use the shortcut where you eliminate this x in the denominator, and that gives you x squared divided by 0.4 equals 5.56 times 10 to the negative 10th. And then when you solve for x, here I get 1.49 times 10 to the negative 5th. Okay, now what did we figure out? What does x represent? We'll take a look at your ICE table. It is, of course, the concentration of ammonia, but that's not the thing that influences pH. It is the concentration of hydrogen ions. And I want to get to pH, and pH is solved by taking the negative log of your concentration of hydrogen ions, which is what I just did by solving for x. So I'm going to take the negative log of that number, and I get 4.8. And it is an acidic solution. All right. Next up, metal cation salt hydrolysis. So you will get to see, okay, just kidding. Before we move on to metal cation salt hydrolysis, what if we've got a weak and a weak? So everything that we've considered so far, you've got a strong and a weak. But if the salt has a cation that is from a weak base and the anion of a weak acid, well then it kind of depends, and you have to compare your Ka and your Kb. The pH of your solution, so if you've got a weak acid and the cation and the anion, they're both weak, they kind of come both come from weak parents. The pH of the solution is going to be neutral if the Ka and the Kb are the same. Basic if your Kb is greater, acidic if your Ka is greater. So for instance, here we go, ammonium cyanide. So ammonium is the cation is from a weak base, and cyanide, that is from a weak acid. So what do I mean when I keep saying like parents and things like this? Well, for instance, ammonium is kind of related to ammonia. So the cation is from a weak base. Cyanide is related to HCN. So if I put a hydrogen on this, I get a weak acid. If I remove a hydrogen from this, then I get a weak base. So here's where everything's weak and weak. The Ka value for this, I'm going to have to figure that out. Hold on. Here's what I have to do. You're going to have to look up the Kb value for NH3, because that's what the ammonium is related to, and that's 1.8 times 10 to the negative 5th. And if I look up the Ka value for the acid, that is 6.2 times 10 to the negative 10th. Okay, so now what I want to do is kind of compare these two particular things. So let's just kind of start with this Kb. So what would the Ka be? What would the Ka be of this particular Kb? What is the Ka version for the NH3? Because this is the salt up here. Well, I'm going to use my Kw relationship. Okay, so Kw is 1 times 10 to the negative 14th. Kb, 1.8 times 10 to the negative 5th. And this comes up to be 5.56 times 10 to the negative 10th. Now, if I go back up here and I look at my solutions, notice that my Ka, 5.56 times 10 to the negative 10th, my Kb, 1.8 times 10 to the negative 5th. Well, this is where you're seeing that your Kb is greater than your Ka. Now, you really don't need both of these, but I looked at both of these values just to kind of show you it doesn't matter. Depending on what problem you have and what table you're reading from, you can either work with the Ka or the Kb of either one of these things. But just to kind of show you that you're going to get the same answer if I use the cyanic acid. 6.2 times 10 to the negative 10th, which gives me a Kb value of, let's see, 1.60 times 10 to the negative 5th. So again, you see how the Kb is larger than the Ka. So that's when you decide, that's going to tell you that these are going to be a basic solution. Okay. Now on to the metal cation salt hydrolysis. So what you guys are going to be seeing are these pretty unusual looking compounds using a metal cation, so like iron or aluminum. Sometimes you get them with copper or beryllium, but not at all with anything with a +1 charge, but usually with these +3 charges. So what kind of happens is because you've got these 3 extra electrons, it's lost 3 electrons, sorry. So it's lost 3 electrons, and you'll see them kind of represented like this, where you've got iron and water, and they form these very funky looking complexes. A lot of transition metals do this, especially the ones with +3 and +2 charges. So what happens with these things is they will react in the water and form this. Okay. Now, AP is not usually going to expect you to be able to come up with these complexes kind of on your own, but you will see them, so you have to kind of know how to handle them. So what this looks like, and I'm just going to kind of draw you a little structure. So if you've got your iron ion, so think like iron 3 nitrate or something like that, when that dissociates, these water molecules kind of become attracted to this positively charged metal. And so in this particular case, we've got the iron complex, and these 6 waters are attracted to it. So that's what kind of, whoops, my OH kind of goes like this. There we go. That's supposed to be water, trust me. So what is happening? How do you tell if this is going to become an acidic or a basic solution? So remember your Lewis dot structure of oxygen, of water here. So the difference in polarity between these two elements, so the oxygen really wants the electron. So it ends up ripping, so it pops off this hydrogen ion, and so you end up with like a hydroxide. And really, if you look at the auto-ionization of water, this is kind of the full story of it as well. You end up with a hydroxide ion and the hydrogen ions. So the hydrogens dissociate, which would tell you that it's going to be an acidic solution. Now the OHs are still going to be kind of attracted over here, which is why it forms this particular complex. But since you have way more of these hydrogen ions, that these things actually form acidic solutions. All right, last topic. Well, and this table's in your textbook and it sums it up pretty nicely. It's not in your notes packet, but is a nice little guide to kind of help you see examples of if something is acidic or basic. And here is that metal ion thing that I was just talking about. Okay, so last little thing. You have weak acids, you have strong acids, but within the weak, some are weaker than others. Within the strong, some are stronger than others. So you have to be able to relate this to strength, to trends, and be able to explain why. Binary acids, so if you remember what a binary acid, that's made out of two elements, just hydrogen and something else. You see the trend of increasing in strength across the period from left to right. So H2S is weaker than HCl as you move from left to right across the period. You also see, as you go down a group, an increase in strength, HF, HCl, HBr. Now the reasons why is you want to think about electronegativity, because remember, if something is a strong acid, that it will dissociate. So the better something can dissociate, split, the stronger the acid it's going to be. So HF is not going to split as much as HCl due to the differences of electronegativity. It is easier for the hydrogen to pop off from the chlorine than it is for the hydrogen to pop off from the fluorine. So you see an increase in strength that way. The other thing you see is an increase in strength with oxygen acids, with oxyacids we call them. The strength again here is based on the ease with which that hydrogen ion is released from the hydroxide group. And again, it comes down to the idea of electronegativities. So across that central ion. So you have to look at the whole molecule, and maybe sometimes drawing the little Lewis dot structure might kind of help you see it better. If they all have just one oxygen, then you see this particular trend here where it increases from bottom to top. So, and you know, if we're kind of thinking about what this particular molecule looks like, you got the chlorine over there, and the hydrogen is attached to the oxygen there. It's not that the hydrogen is coming off the chlorine. If you have more oxygens, the more oxygens you have, the stronger it is. Why? Because that oxygen and that increased electronegativity makes the overall molecule more polarizable, which makes the hydrogen ion ionize easier. So the more polarizable the molecule is, in other words, that electron density cloud type of idea, where all the electrons are being pulled kind of in this direction, then that hydrogen is going to go woo and kind of pop off. And the more hydrogens you can liberate from the compound, the stronger the acid would be. So all these nice little charts kind of help summarize those types of ideas and help you see why is it that this is considered a strong acid, and this is a strong acid as well, but not as strong as perchloric acid. So chloric acid, perchloric acid. But as soon as you start changing your number of oxygens, oops, not that one. As soon as you start changing the number of oxygens, you will see differences in the strength of, that's what I was trying to do. You'll see the difference in the strength of the acid. Same thing between sulfuric and sulfurous. So notice the difference is one oxygen. This is a strong acid. This is a weak acid. This is a strong acid. That's a weak acid. Strong, strong, weak, weak. So the less oxygens you have, the weaker the acid. Here are the halides. So the stronger the bond, the weaker the acid. The less that hydrogen is able to dissociate, able to ionize. And I put this little picture up here just to kind of help you see where these hydrogens attached. All right, that is it for chapter 14. Have a great day. Bye.